This episode is sponsored by the book. In early 1951, the United States Air Force had a problem it couldn't solve on its own. In Korea, American bombers were being lost at a rate the force couldn't sustain. Not because the crews were untrained, but because the aircraft they were flying had been designed to fight the last war. What they had were either too slow or lacked the endurance to fly night interdiction missions over mountains against supply routes that reopened every time the sun went down. What the Air Force needed already existed. The issue? It just wasn't American. On a cold February morning at Andrews Air Force Base, a straight-wing British bomber built by a company better known for locomotives than combat aircraft was about to do something that seemed almost impossible. Not in theory, not on paper, but where it mattered, in the air. What followed was not a technical failure or a political scandal or even a bad decision made in haste. This is the story of an aircraft that was good enough and an institution that needed it to be perfect. And welcome to Aviation Republic. My name is Joe. Right, before we get into the story, I just want to say a big thank you to Hungry Minds for sponsoring this episode. They've released this book, simply called The Book, The Ultimate Guide to Rebuilding Civilization. Now you might be thinking, Joe, why do I need this? Well, if you're anything like me, you'll appreciate the attention to detail that's gone into making it. It's gorgeously put together. Premium paper, medieval meets engineering illustrations, and a hardcover you'll want to display. Although I keep mine in the box it came in, which I like to pull out when friends come around. I can't help but show them, though I do make sure they've washed their hands first before I allow them to stroke the embossed cover. The book is made up of over 400 pages on how to restart society if everything goes sideways. Fire, medicine, metalworking, engines, even building aircraft, with hand-drawn diagrams showing wings, propellers and control surfaces. Because when civilization collapses, you won't have the luxury of YouTube to show you how to start a fire or build a steam engine. So if you'd like your own copy, use code AVIATION for 10% off. Link in the description or scan the QR code on the screen. Once again, thank you to Hungry Minds for sponsoring this video. They keep the tea flowing and the biscuit tin full. And who knows, the way things are going, we might just need this sooner than we think. Andrews Air Force Base, Maryland, February 26, 1951. Picture yourself in the tower at Andrews that morning. Crisp, clear day, high overcast, perfect flying weather. You're part of the Senior Officers Board with representatives from Headquarters USAF, Tactical Air Command and Air Defense Command beside you. There are 5 aircraft on the ramp below. One of them needs to solve that impossible problem. Here's your situation. In Korea, Douglas B-26 invaders are being lost. Attrition projections suggest the entire infantry will be exhausted by 1954 if the war continues at this pace. But losses aren't the real problem. The real problem is mission failure, specifically night interdiction, stopping North Korean supply convoys after dark. The B-26 can only attack during the day, which means when the sun sets, the supplies flow and your bombers achieve nothing. Every night those routes reopen, the war lengthens and casualty lists grow elsewhere. You need something faster, higher, with endurance to actually loiter over supply routes rather than making quick passes before turning home for fuel. Here's what you have. The Martin XB-51, fitted with 3 armor-protected General Electric J-47 engines that can push it to over 600 miles an hour. A strange-looking machine, but genuinely impressive, although technically complex, with variable angle of incidence wings that pivot to increase the angle of attack for takeoff and landing, and fitted with a revolutionary rotating bomb bay. But it's also heavy, with a high wing loading and needing a considerable amount of runway to get into the air without rocket assistance. And on top of that, it can only loiter for 1 hour at a time with a combat radius of just 800 nautical miles. Robert Mikesh, a former B-26 pilot and aviation historian flying combat missions over Korea, had made it clear what was needed: an aircraft that can carry more bombs and remain longer over supply routes. The North American Tornado, with its 4 jet engines, is already obsolete World War II technology in a jet wrapper, but for now at least it's a valuable reconnaissance asset over Korea. So we have speed without endurance and altitude without agility, exactly the wrong trade-offs for this war. The other 2 aircraft on the apron that morning, the AJ-1 Savage and the CF-100 Canuck, aren't really serious contenders as being either too slow, too small and not enough range. And then there's the English Electric Canberra, British, straight-winged, built by a company better known for domestic appliances and trains than combat aircraft. On the ramp, it looks simply antiquated, supremely ordinary looking next to the XB-51, like something from 1945, certainly not belonging beside the swept-wing modernity of the American designs. If the XB-51 was a heavily armoured sprinter, the Canberra was a nimble marathon runner. A strong Air Force faction prefers the XB-51 because it's American. In fact, the Air Research and Development Command had already listed no less than 31 major deficiencies the Canberra would need corrected to meet USAF standards. Not a great start. And this fly-off exists less to inform the Air Force than to reassure the Senate that every alternative has been exhausted before accepting a foreign aircraft into American inventory, which hasn't happened since the First World War. The briefing for the comparative display is strictly formal and by the book. Each aircraft will fly the same set pattern of simple maneuvers in a 10-minute time slot. Roland Beaumont is the only foreigner present. All the other pilots are Air Force or American company test pilots. When he asks if the patterns could be varied to suit particular aircraft, the answer comes back firmly. No, this is an Air Force trial, not a Farnborough air show. Which is a shame, as nobody particularly wants to be there that morning watching an American design potentially lose to a British aircraft. The B-45 Tornado goes first. Its routine is adequate but unimpressive and is quickly dismissed. Its design considered stodgy and outdated, with little potential for performance growth needed for low-level night tactical operations. The Martin XB-51 goes penultimate. Fast in a straight line, over 100 miles an hour faster than a Canberra, but with its comparatively high wing loading, its manoeuvrability is severely limited, and it's also twice the cost of the British machine. Within Andrews boundaries, it can't pull off the sort of turns the mission actually needs. Then it's Roland Beaumont's turn. Together with a USAF evaluation officer, he climbs into Whiskey Delta 932, fires up the 2 Rolls-Royce Avons and lines up, pushes the throttles forwards and starts his takeoff run. Rotation at 80 knots, nose up into a 45-degree climb at 150. The straight-wing bomber that looked conventional on the ground is climbing like a fighter, the 2 Avons pushing upward at an impossible angle. Beaumont pulls her around for a high-speed pass, followed by a series of Type 4G turns. The low wing loading allows Beaumont to fly the entire set pattern inside Andrews Air Force Base perimeter. Another turn at 2.5 Gs, smooth and controlled. Then a slow flyby at 110 knots, gear and flaps down, Beaumont showing off the confidence he has in the aircraft across his speed range. The routine is supposed to last 10 minutes, but Beaumont completes the set pattern in only 6. So he has 4 minutes remaining. Should he land? With no one having advised what to do with any remaining time, he retracts the undercarriage, opens up the taps on the Avons, raises the flaps and pulls into a tight 360-degree turn over the assembled observers. Half roll into a high-speed low pass, pull up into a climb followed by a wing over, then throttles to idle, air brakes out into a tight spiral dive. To pull out and whistle almost silently past the spectators and glide into the landing pattern with just a gentle touch of throttle to line up with the runway. What Andrews ATC hadn't mentioned, because of the recent icy conditions, the white concrete runway had been covered with a fine layer of white sand, white on white, invisible to a pilot on approach. Whilst braking, both main wheels lock, causing the tyres to burst. The USAF evaluation officer seated in a navigator's seat as observer is so overawed by what he's just been put through that the tyre burst incident goes virtually unnoticed. But this wasn't the first time the USAF had encountered the Canberra. A committee led by Brigadier General Albert Boyd had inspected the aircraft in England and had concluded that it was superior to any current or contemplated USAF all-weather bomber. Superior to anything American, current or contemplated. And that's the Indignity. The question was never whether the Canberra worked, but whether it worked the way the United States expected its bombers to fight. But Korea is happening now. Aircraft and crew are being lost now. Supply convoys are running every night and those casualty lists keep growing. The board will conclude that the Canberra, and I quote, comes closest to filling the night intruder profile because of its excellent characteristics of endurance, range, maneuverability, and the visibility provided from the nose section. The assessment was unambiguous. No aircraft, American or otherwise available off the shelf, could come anywhere near what the Canberra delivered. Not slightly inferior, not needs more development, nowhere near it. That reality, that the first foreign aircraft purchased since 1918 wasn't a compromise, but genuinely superior to every domestic alternative, created political pressure that would shape everything following. The institution needed to show that while British design was acceptable, American specifications remained necessary. That good enough for the RAF wasn't good enough for the USAF, and the modifications to come weren't admissions of defeat but proof of higher standards. Whether those standards could produce a better aircraft or simply a more complicated one remained to be seen. The Andrews demonstration made the choice look obvious, but it wasn't. 3 months earlier, an evaluation committee had recommended a split purchase. Buy Canberras now for immediate operational need, give Martin time to perfect the XB-51 as the long-term solution, then replace the Canberras once XB-51 production proved itself. The senior officers board rejected that compromise. They suspected the evaluation committee favoured the XB-51 because it was American. That suspicion probably had merit. The endurance or lack of was a problem. The XB-51 could only loiter 1 hour over targets 350 nautical miles from base, whereas the Canberra could manage 2.5 hours of loitering at 780 miles range. For night interdiction over Korea, the Canberra's endurance advantage was decisive. Also, the XB-51's distinctive wingtip wheels would need special handling at forward bases, whereas the Canberra worked anywhere. And to top it off, the XB-51 is also twice the cost of the British machine. It was clear that the Martin aircraft couldn't deliver what Korea needed, not now and maybe not for years. The decision was made, but the doubt never quite left. However, the English Electric's production lines were already committed. 4 British plants were producing 13 or 14 Canberras per month, impressive by 1952 standards, but author Bill Gunston would later note that it betokened a crippling rundown in productive capacity. During the war, Britain had produced 400 heavy bombers monthly despite material shortages and enemy action. RAF orders had the factories at capacity, and accommodating American requirements on American timelines with American changes was not realistic. Even if the Air Force had wanted British-built aircraft, there simply weren't any available soon enough. The compromise is elegant. License build it. March 23, 1951, less than 1 month after the demonstration, the Air Force requests Martin to produce 250 aircraft. American company, measurements, components. Correct the deficiencies the Air Development Center believed it saw, make it American, make it better, make it ours. We're not buying British, we're improving it. That conviction that an aircraft which already worked was to need over 2,800 engineering changes and would define the next 20 years. Sometimes the indignity isn't in admitting you need help. Sometimes it's in refusing to believe that the help doesn't need fixing. I want to take a second here to thank you so much for watching. I'm truly grateful to share my love of aviation with fellow enthusiasts like you. So if you're enjoying this story, please take a quick second to hit the like button. It's a small gesture that makes a huge difference in helping me reach more aviation fans. Now let's get back to the story. While Martin engineers in Baltimore were working through the list of deficiencies, Royal Air Force squadrons were flying the Canberra operationally. Number 101 Squadron at RAF Binbrook received their first aircraft, Whiskey Delta 936, on May 25, 1951, just 3 months after the Andrews demonstration. Crews transitioning from Avro Lincolns found the Canberra extraordinary. Nearly double the speed, 3 times the service ceiling, and handling that felt more like a fighter than a bomber. Pilots were qualifying after as little as 3 hours of familiarization flying. The aircraft simply worked. Which raises an obvious question. If it already worked, what exactly were the Americans about to fix? To understand that, you need to understand the design philosophy of Teddy Petter, the man behind the Canberra, a philosophy which he called adventurous conventionalism. Now, this sounds like a contradiction. How can you be both adventurous and conventional? But that was precisely the point. Petter had understood that swept-wing designs struggled with transonic aerodynamics, designs which added weight and complexity to solve problems that might not exist if you simply didn't fly that fast. His solution was straightforward. Design the aircraft operate in the Mach 0.7 to 0.8 range, where the aerodynamics were well understood, the structures were straightforward, and the performance was more than adequate for the mission. The wing he chose was deliberately unswept with an enormous chord, 19 feet from leading edge to trailing edge inboard of the engines. In a 1953 interview, he explained, "The wing we chose was a fair compromise, excellent altitude performance in a simple, cheap, easily built aircraft. With the thrust available from early Avon engines, sweeping the wings would have been pointless and would have merely added weight while reducing maneuverability. Everything about the design prioritized simplicity over sophistication, and nowhere was that more evident than how the wing attached to the fuselage. The British called it a simple 2-bolt affair. Each wing's main spar, a strong webbed forging made from DTD683 aluminium alloy with a tensile strength of 32 tons per square inch, attached directly to the center fuselage through 2 massive bolts. The load path was clean, the forces distributed efficiently, and the entire structure had been analyzed and proven adequate for an ultimate load factor of 7.5 Gs. By February 1951, the first of many hundreds of production B-2 aircraft were flying. The service record was unblemished with no structural failures. British engineers had concluded the airframe could achieve 20,000 hours without major structural modification. 20,000 hours on 2 bolts per wing. American engineers at Wright Air Development Center looked at this and saw a shortcoming. Not because it had failed, it hadn't, but because it didn't meet their standards for redundancy and fatigue life, and had been listed as one of the 36 deficiencies that were believed needed fixing. The Americans would redesign it as a 4-bolt affair, and this would mean increased complexity, more weight, and considerably more expensive. The British position was blunt. The redesign would never prevent a single failure the original wouldn't have handled. The Americans proceeded anyway. In July 1951, Glenn Hobday arrived at Martin's Middle River facility, representing English Electric throughout the license production process. Back in England, he'd been the chief technician, the gentleman running the design studies and wind tunnel work. His actual job at Martin turned out to be watching his company's design get systematically rebuilt. By the time Hobday arrived, work had already begun on what engineers call a tremendous redrawing job. Every drawing converted from British standards to American sheet metal gauges, every rivet specification redrawn, every bolt recalculated. Fair enough, logistics matter. American supply chains couldn't stock British fasteners. To meet their production schedules, Martin subcontracted a great deal of the B-57, and to be sure that all the parts would fit seamlessly together, English Electric sent over photo loft-in plates that were worth the license fee alone. Traditional aircraft manufacturing needed physical patterns, wooden forms defining every curve, every compound surface. Subcontractors needed access to master patterns to prevent quality variation. English Electric's photo loft-in captured 3-dimensional surfaces onto 2-dimensional photographic plates with precision measured in thousandths of an inch. Martin distributed these plates to Kaiser, Hudson Motors, Cleveland Pneumatic Tool Company, so any subcontractor with these could manufacture the complex curved parts from copy plates without ever seeing a physical pattern. But the measurements were just the beginning of something larger, the systematic replacement of design philosophy with procedural compliance. The 2-bolt wing attachment wasn't an isolated choice. It represented Petter's approach to the entire aircraft. Optimized for the mission, accept what works, don't add complexity that operations don't need. That philosophy showed up everywhere, but most visibly in the wing itself. The Canberra B-2 had a wing area of 960 square feet and a maximum takeoff weight of 46,000 pounds, giving it a wing loading of 48 pounds per square foot. Compare that to the Douglas B-26 Invader at 66.7 pounds per square foot, the North American B-45 Tornado at 81.4, and the Martin XB-51 at 116.5 pounds per square foot. Lower wing loading means more wing surface relative to weight, which translates directly into tighter turning radius and better high altitude performance. At Andrews, when Roland Beaumont pulled that Canberra into 4G turns within the airfield boundaries, he wasn't showing off. Well, maybe a little. He was demonstrating what 48 pounds per square foot could do that 116.5 couldn't. At 50,000 feet where the air is thin and lift is difficult to generate, that enormous swing gave the Canberra the same turning ability that a Gloucester Meteor fighter had at 40,000 feet, enough to evade anything that managed to climb that high. Even the contemporary MiG-15s had practical combat ceilings closer to 40,000 feet and suffered rapidly deteriorating handling above that altitude. As though to prove that point, that summer Beaumont delivered the second pattern aircraft, Whiskey Delta 940, setting a transatlantic speed record while doing it in only 4 hours 18 minutes from Aldergrove to Gander, averaging 481 miles per hour. On the second leg to the Martin factory in Baltimore, New York Air Traffic Control asked repeatedly for his altitude. British security procedures classified such information, but the Americans kept asking as Beaumont approached Long Island. He checked fuel state with his navigator Watson and then advanced to climb power and took the Canberra to 50,000 feet. The following day, a meeting was held at the Pentagon with what Beaumont later described as a room full of senior officers festooned with considerable amounts of ribbon. The discussion covered the Canberra's performance and flight characteristics, all very formal until someone finally asked, "There seemed to be some communication problems yesterday. What height were you over Long Island?" 50,000 feet, Beaumont confirmed. The response was audible astonishment, a few gee whizzes and whistles. When it subsided, one officer noted that air traffic control needed altitude data for safe separation of aircraft. Beaumont responded, "Certainly, but there weren't going to be any other aircraft up there, were there?" The thrust-to-weight ratio further reinforced the Canberra's performance advantage. The two Rolls-Royce Avon RA3 engines produced a combined 13,000 pounds of thrust, pushing 46,000 pounds of aircraft to give it a thrust-to-weight ratio of 0.28. The B-45 managed 0.22. The XB-51, despite its 3 engines, achieved only 0.24. That extra thrust meant reaching 50,000 feet in roughly 15 minutes. In combat, that translated directly into survivability. The Canberra could outclimb and outmaneuver contemporary fighters at altitude because it had the power and the wing area to do it both simultaneously. Perhaps Petter's most enduring contribution was the modular construction philosophy. The aircraft was designed as 5 independent primary structures: front fuselage, center fuselage, rear fuselage, and 2 wing sections. Each module could be manufactured at different sites using standardized jig techniques, then married together at final assembly. You need a photo reconnaissance version? English Electric extended the front fuselage by 14 inches. The PR3 was born without redesigning the entire aircraft. Require a trainer variant? No problem. Replace the bomber nose with dual control section, and here is the dual control T4. Low level interdictor, you say. One moment, I'll graft on a completely redesigned forward fuselage and the BI-8 rolls off the production line. But modularity meant that entire sections could be swapped if damaged, a capability that would prove its worth decades later under conditions Petter never anticipated. The Canberra worked because 46,000 parts fit together in a way that prioritised operational simplicity over manufacturing convenience. British engineers accepted what they called living with the roughness. It was good enough. It worked right now, not 3 years from now after another round of wind tunnel testing. However, every British solution that worked without meeting American specifications represented a precedent. If the 2-bolt attachment were accepted, what message did that send to domestic contractors? If foreign control systems bypassed various requirements, how could the Air Force enforce those standards on Boeing, Douglas and others? The Canberra was a test case for whether operational proof could override institutional standards. The Americans had documents, mil-spec, military specifications that described how to build aircraft for the United States military. The British had their own equivalent, AP970. Both worked, they simply weren't the same document. However, institutional dysfunction wasn't uniquely American. While Martin engineers were implementing the thousands of modifications to satisfy Air Force demands, the British Treasury was practicing what many called the drip feed system, buying everything in the smallest possible quantities, forcing manufacturers to justify every trivial expenditure. In 1945, English Electric received orders for 90 Canberras, then 75 more in 1950. The RF requirement was for 400 aircraft, but the Treasury wouldn't commit to buying large amounts up front. There is a quote from Bill Gunston in his book Bombers of the West that sums up the attitude of the Treasury at the time. Rather like the housewife who saves money by buying everything in the smallest possible quantity, ending the year having spent more than a bulk buyer with a deep freeze. Different institutions, different dysfunctions. The British couldn't plan production because the Treasury was penny pinching. The Americans couldn't accept proven aircraft because specifications demanded compliance. Both approaches cost more than necessary whilst claiming to save money. The British Canberra development would later suffer its own specification creep as successive variants absorbed new requirements just as American ones did. The flight control system was Hobday's example of what he'd later call political window dressing. The Canberra used push-pull rods, simple mechanical linkages, transmitting pilot inputs directly to control surfaces. The British had designed them to give pilots the right feel through the controls while staying structurally rigid under stress. The system was robust enough that Hobday had never known a pilot to break the controls through physical effort, even in violent maneuvers. The Americans ripped it all out and installed cables. Not because the push-pull system failed, not because pilots complained, because United States military specifications required cable-based flight controls, and the requirement focused solely on pilot load, completely ignoring the stiffness considerations the British had built in. The modification made institutional sense. Cable systems were familiar to American maintainers, standardized across the fleet, and simplified training. It just didn't make the aircraft fly better. Jess Sweetser, Martin's vice president for sales, would later assess the Americanization program with brutal honesty. Out of 2,800 engineering changes, I reckon 2,700 of them have been made just to comply with US standards. There's been a massive waste of effort here. How's about our two countries trying to get together a bit? So, nearly 3,000 changes just to comply with standards, not to fix problems or improve performance, just to comply. And Sweetser's assessment came from inside the program whilst it was all happening, not decades later with hindsight's clarity, but in real time whilst Martin engineers were implementing modifications. Then there was the oxygen system. The Americans wanted to save weight, so they specified liquid oxygen instead of the British gaseous bottles. Sensible on paper, LOX weighs less for equivalent capacity. In practice, the LOX system needed factory-like facilities to recharge, undermining the operational flexibility the original design had assumed. Weight saved, flexibility removed. Hobday documented it all through the Combined Test Project Agreement, the formal arrangement between the United States and the British mandating information sharing on aircraft development. When English Electric developed an improvement, Hobday passed it to Martin. When Martin developed an improvement, the agreement required it to flow the other way. except most of what the Americans called improvements weren't improvements at all. The aerodynamic cleanup work, stiffening the rear fuselage, sealing the aft bulkheads, closing the gaps around the stabilizer, came from the British wind tunnel data Hobday brought from England. Martin engineers implemented, then claimed credit for cleaning up the British design. The tandem cockpit arrangement that would define the B-57B, English Electric had already studied the concept. The files were sitting in Hobday's briefcase when he arrived at Middle River. Most changes were minor on paper, but taken together they were reshaping how the aircraft behaved and was maintained. Hobday's assessment was more succinct: a waste of time. Mil-spec wasn't designed to produce better aircraft, it was designed to produce predictable fleets, aircraft that American maintainers could service, American logistics could supply, and American doctrine could integrate without creating precedents that undermine standards across Boeing, Douglas, Lockheed and others. The effort wasn't wasteful from the institution's perspective, it was insurance against congressional questions about why taxpayer money went to aircraft that didn't meet US specifications. Wright Air Development Center demanded compliance with mil-spec. The Air Research and Development Command demanded corrections to the list of deficiencies. Headquarters USAF had final approval. The Martin Company, caught between their British design and American requirements, did what contractors do: re-engineered the problem to satisfy the customer. But right now, the question on the minds of everyone at Martin was, had the British built something genuinely good? They were about to find out. Middle River, Maryland, spring 1951. Orville Edwin Pat Tibbs walked around the British Canberra sitting on the company ramp and tried not to let his face show what he was thinking. Straight wings, not swept. That bubble canopy, broad and exposed. On the ground, it looked conventional in the way that contemporary swept wing designs weren't. Tibbs was Martin's director of flight, which meant if Martin built it, Pat flew it first. He'd been doing that since before the war. Maryland's, Baltimore's, every type that followed. Right now, the situation was complicated. Martin had just lost the tactical bomber competition to this aircraft. It was inconceivable that their fast trijet swept-wing XB-51 was beaten by this. Surely there must be some mistake. The factory workers were disgusted. President Chet Pearson had called it a personal insult. George Maverick Bunker, soon to be Martin's president, would later say, "Frankly, we were disgusted. Building a foreign plane was something our industry had never done, and a lot of us took it almost like a personal insult. A poor reward for a lifetime of service to the US military." But Martin couldn't afford the luxury of wounded pride. The company was bleeding money. The production of the 404 airliner had stalled. Aircraft sitting incomplete meant payments not received. By December, the Mellon Bank would force Glenn Martin aside, install new management, place the founder's shares in a voting trust. The company he'd built since 1909 would be run by bankers and their chosen executives. The Canberra, or B-57 contract was humiliating, but it was also keeping the lights on. The Canberra was exactly the kind of trouble-free work which we badly needed, as Bunker admitted. Now Tibbs had to fly the thing that had humiliated them. Wing Commander Roland Beaumont from English Electric handled the briefing, very frank about both the good points and the doubtful qualities. High-speed buffeting at 0.83 Mach, rudder overbalance issues in early testing. Tibbs listened carefully, made notes, asked technical questions. What he didn't mention was his private opinion of British engineering standards. Before the flight, he joked to colleagues that he was somewhat dubious about the British method of determining limit buffeting values. He suspected their limits were probably based on the point just before the aircraft completely disintegrated. Then Chet Pearson pulled him aside. "Pat, if you like the aeroplane at all, do a slow roll or something when you bring it home. The morale is pretty low here for us, having designed our own plane, yet have to build a foreign design." Fair enough. Tibbs climbed into Whiskey Delta 932, serial number stenciled on the nose, and spent time getting familiar with what Beaumont called the gadgetry. British instruments, British systems, British thinking throughout. The control yoke felt a little odd, but the visibility was excellent, he'd give him that at least. Engine start, cartridge ignition fired, ejecting a plume of smoke, the twin Avons spilled up with that distinctive whine. Taxi checks were completed and he was cleared for takeoff. As instructed, he rotated at 80 knots, the nose coming up smoothly, and with that he commenced his climb to altitude. At 30,000 feet he pushed past 0.8 mark and felt the airframe start to buzz. Severe roughness as briefed. He backed off, made notes, climbed higher to test handling at altitude. Confident of its feel and maneuverability, he found that he actually liked the aeroplane. Before long, it was time to go home. The workers on the ramp at Middle River watched as their chief test pilot brought back the foreign aircraft. And with Pearson's request still echoing in his ear, Tibbs brought Whiskey Delta 932 screaming across the field at 400 knots 10 feet off the deck. At the far end of the runway, he pulled into a steep climb, rolling inverted at the top. Then, without warning, both Avons flamed out. For several long seconds, Pat Tibbs was flying a high-speed glider, inverted over Baltimore. But with a light fuel load, plenty of altitude, and what Martin engineers would later call cool thinking, he rolled upright, working the relight procedure Beaumont had briefed. First engine caught at 800 feet, then second engine relit. With power returning, he brought the nose back around towards the field for a conventional and graceful touchdown. Taxi to parking, engines shut down. Tibbs climbed out, flight suit damp with sweat from the heat under the canopy, and told the gathered engineers exactly what he thought. I can detect no difference between this aircraft and what we expected in takeoff, climb out, or cruise. He paused, choosing his next words carefully. I reached 0.83 mark up there, severe roughness, that's where I stopped the speed investigation. The British have built something that handles well within its limits, but those limits exist for a reason. His assessment satisfied the engineers, the aircraft worked. The flame-out recovery had proven the systems were robust. The British design was sound. Pat Tibbs had validated that the British had built something that worked and was good enough. The factory workers who'd watched the whole thing weren't disgusted anymore. At the Wright Air Development Centre, the engineers weren't asking whether the Canberra worked. They were asking whether good enough was acceptable. December 21st, 1951, 10,000 feet over Delmarva Peninsula, Maryland. Major Harry Lester is flying Whiskey Delta 932 with Captain Reed John Shaw in the back. This is the same aircraft Pat Tibbs had flown that spring. He's pulling 4.8 Gs at 420 knots in a tight turn, his instruments saying he's well within limits. But something's not right. The turn is tightening even though Lester's not pulling any harder on the yoke. Something's definitely wrong. The actual G-load is climbing towards 7 when suddenly the left wing spar fails just outboard of the engine nacelle, overstressed beyond its design limits and breaks away. Lester pulls the ejection handles and his seat fires through the canopy. This is the wrong procedure for that altitude as it should have blown off first, but he survives with minor injuries. Behind him in the coal hole, Captain Reed John Shaw ejects through his overhead hatch. His parachute fails to open. The inquiry was thorough. The investigators found that a fuel sequencing error had been the cause of the crash. The forward tanks had been consumed first, shifting the center of gravity far beyond limits. The tail heavy aircraft turned what instruments showed as 4.8 Gs into actual loads investigators estimated between 6.5 and 7 Gs, explaining why the turn had tightened on its own. Under those uncontrolled, unstable conditions, the wing spar failed. In the UK, Roland Beaumont flew the same maneuver at higher speeds and higher G loads without incident, proving the design was sound when operated within its proper centre of gravity limits. But the incident had claimed Captain Shaw. His parachute failed to open after ejection. The cramped coal hole, already controversial for poor visibility and complicated emergency egress, became impossible to defend. Whether Shaw might have survived with better egress provisions remained unknowable, but one fatal accident made questions about crew safety impossible to ignore. One procedural error had created the political leverage that technical findings couldn't overcome. The modifications that Wright Air Development Center had been planning since March would now be impossible to stop. Middle River, Maryland, July 20th, 1953. Pat Tibbs straps into B-57A serial 521418 with George Rodney beside him recording engineering data. It's been 28 months since Martin signed the contract to build the aircraft. Now the first one is ready to fly, fitted with British ailerons straight from English Electric over in Preston, England. Martin had subcontracted aileron production to Kaiser, who'd been given the photo loft-in plates. However, theirs must have been slightly out of focus because when their ailerons arrived at Middle River, they refused to fit into Martin's wings. English Electric rushed replacement ailerons from Preston by air. These fitted perfectly, manufactured using the original jigs that had already produced hundreds of Canberras for the RAF. This aircraft was fitted with the Wright Aeronautical J65 engines. These were American-built Armstrong-Siddeley Sapphires producing 7,200 pounds of thrust each. These were fitted instead of the Rolls-Royce Avons. The engine choice came down to timing and money. Wright Aeronautical paid almost $500,000 for the manufacturing rights, then subcontracted initial production to Buick Motors. The Buick-built engines carried the designation the J65BW2, and when they started arriving at Middle River, they created problems nobody had anticipated. After the first few B-57As rolled off the line with Buick power plants that weren't quite right, Wright took over full production themselves with the J65W5 designation. The extra thrust, the 7,200 pounds against the A16500, compensated for American modifications that added weight the British design never anticipated. The Sapphire's larger front casing diameter meant visibly bulged nacelles compared to British production aircraft, something spotters would notice immediately on the ramp. The A1 had proven itself superior in several ways. Smokeless starter cartridges, or at least as smokeless as they could be, from the beginning meant no dense black clouds during engine ignition, and triple breech starters provided immediate backup if the first cartridge failed, rather than pulling the starter for maintenance. But the Sapphire was available when production needed to start, and Wright's licensing terms worked better than what Rolls-Royce was offering. With Korea happening, availability mattered more than future potential. The J65 would prove reliable enough through thousands of operational hours. It wasn't perfect, but it delivered what combat needed. And except for these different engines and the 2,000 or so modifications, it was essentially what Roland Beaumont demonstrated at Andrews in February 1951. This first flight was methodical. Systems validation, handling checks, 46 minutes aloft testing what 2 years of engineering changes actually delivered. Tibbs' assessment lands precisely where the engineers hoped. Performance virtually indistinguishable from the British original. The increased thrust compensates for the added American weight. However, takeoff climb rate hits 5,700 feet per minute, 50% better than the British B-2's 3,800 feet per minute, so there was that. Speed touches 590 miles per hour with a service ceiling exceeding 53,000 feet. Performance virtually matched the British original whilst validating those American modifications, so the aircraft works. But 7 days later, on the 27th of July 1953, the Korean War Armistice was signed. The very war the aircraft was built to serve was over. On the 20th of August, Martin presented the first American-built B-57A Canberra serial 521418 to the United States Air Force, who then immediately bailed it back to Martin for continued testing. Of the 250 aircraft the original contract had specified, the Air Force accepted exactly 8 B-57As total. Not 8 of 250, 8 total. The institutional assessment was blunt. The B-57A is not a combat-ready machine. Serial 521418 validates performance and engine development before eventual transfer to NACA in June 1957. The other 7 dispersed to armament trials, structures testing, stability validation, antenna configuration work. 1 crashes during testing in November 1954. One B-57A, serial 521419, will eventually join the National Oceanic and Atmospheric Administration, modified with storm plotting sensors for Project Storm Fury, operating out of Miami International Airport, tracking hurricanes across the Atlantic. After retirement from NOAA, it becomes a ground maintenance trainer at the George T. Baker Aviation School. The bomber bought to stop North Korean supply convoys ends its service life teaching students how to change hydraulic fittings. None of the 8 will ever deploy to combat zones. The remaining 67 aircraft from that first production batch rolled off the line as B-57As, painted in glossy black anti-searchlight paint, a paint scheme worn by no other American aircraft except the wartime P-51 Black Widow. These B-57As are reconnaissance variants built to fill a requirement that didn't exist when the contract was signed, a capability the Air Force prioritizes because the bomber variant wasn't ready for combat. The 363rd Tactical Reconnaissance Wing at Shaw AFB in South Carolina became the first operator in summer 1954 with their red and white checkered tail marking distinctive on that gloss black finish. The 345th Light Bomber Wing at Langley AFB in Virginia received their first aircraft around the same time. By the end of 1957, the Douglas RB-66B was already replacing them in Europe. Martin's production line continued operating, hitting peak production of 20 aircraft per month by January 1954, exactly as planned, except those aircraft weren't the tactical bombers the March 1951 contract specified for operational delivery. They were development aircraft validating systems that won't enter service until later variants arrive. Serial 521418 sat at Middle River after its first flight. Everything functioned properly. It just arrived too late for the war that justified buying it, too early for the requirements the Air Force actually wants satisfied, and optimized for a specification that evolved whilst engineers were making every measurement American. The program would ultimately deliver 403 aircraft, but Serial 521418 was a clear example of a specific phenomenon. Compliance timelines extending beyond operational urgency, creating gaps where requirements drift, wars end, and specifications evolve into something different than what was ordered. The aircraft worked, the process just took time to catch up. The consequences of that mismatch would only become visible once the Canberra was finally asked to fight. But Korea had shown what was needed: a tactical jet-powered attack aircraft with endurance, short-field capability, and the ability to find targets at night or in bad weather. The Canberra delivered exactly that. When Korea ended in mid-1953, just as Martin hit its production stride, the Air Force pivoted towards global conflict with the Soviet Union. Astronomical funds flowed to strategic bombers and missiles. The need for short-field bombers operating in all weather and darkness seemed mundane by comparison, so it was set aside. Then, Vietnam happened. The Air Force found itself superbly equipped for a war it was not fighting. Aircraft optimized for nuclear deterrence were suddenly asked to perform tactical interdiction. The mission profile that had driven Canberra procurement in 1951 had to be rediscovered in combat in 1965. The B-57s that had arrived too late for Korea were perfectly suited for Vietnam. The institution had built exactly what was needed, forgotten why it was needed, and then had to remember, under fire. Langley Air Force Base, Virginia, October 1954. 15 months after the Korean armistice, the B-57B finally arrives. It's everything the B-57A should have been. Tandem cockpit, rotating bomb bay, forward-firing guns. Robert Mikesh stands on the ramp with the 345th Bomb Group, watching Pat Tibbs climb into B-57B serial 521506, ready to show what years of re-engineering actually delivered. The aircraft that arrived too late for Korea would now prove if it was worth the wait, or so the assembled crews hoped. Roland Beamont's demonstration at Andrews had been spectacular. 10 minutes proving to the procurement board that the Canberra could do things medium bombers weren't supposed to do. Pat Tibbs didn't have that constraint, just the assembled crews who needed to understand what they were about to fly. With a light fuel load, no wingtip tanks, he lifted off in less than 2,000 feet, retracting the gear almost immediately, and the aircraft climbed like it weighed nothing. With the freedom to push through the full operating envelope meant that the assembled crews were seeing what the aircraft could sustain, not just what it could do briefly. At low altitude, without power-boosted controls, manoeuvring the aircraft needed a lot of grunt. On landing, Pat Tibbs climbed out, with his flight suit soaked through, not just from the greenhouse canopy trapping the heat, but from the effort required to hold the nose through manoeuvres that need up to 80 pounds of pull force. His assessment to the assembled crews is specific. Now, the B-57 aircraft you see on the line and that you saw flying this morning resembles the Canberra I just described when I evaluated it in 1951. But believe me, gentlemen, there is no resemblance in the performance today of the two aircraft as far as the high-speed characteristics are concerned. A lot of work had gone into the aerodynamic cleanup, sealing stabilizer gaps with snug-fitting covers, closing aft fuselage bulkheads, and superior aileron sealing. The cleanup work solved problems the British had already figured out, or so the competing stories went. Tibbs described it as an American achievement, the modifications worked, and the severe buffeting at 0.83 Mach disappeared. Hobday, English Electric's resident engineer at Martin, told it differently. The cleanup evolved from British wind tunnel data he'd brought from England. English Electric had identified the problems and developed the solutions. The combined test project agreement required that both companies share improvements. Hobday passed the information to Martin, Martin engineers implemented it, then claimed credit for cleaning up the British design. Roland Beamont flew both British and American variants through their flight envelopes. He considered the modifications cosmetic, and the Canberras back in England had been tested up to 0.84 Mach, and although the buffet was heavy, it caused no problems. Although the B-57B did suffer nose-up trim changes at lower speeds than the British aircraft for reasons nobody quite explained, but a small spoiler along the horizontal stabilizer eventually cured it. Different accounts, different claims about who sold what, but the aircraft worked either way, though the credit always stayed disputed. Ultimately, the B-57B could reach high speed smoothly where the unmodified airframe risked vibrating itself to pieces, though the empty weight had climbed to 28,500 pounds, 6,500 pounds heavier than a British B-2. The rotating bomb bay is its greatest advantage, able to be opened at 500 knots, the aircraft's maximum speed, whereas the British Canberra bomb bay doors were mechanically restricted to just 350 knots. 4 seconds to rotate to the open positions, then 6 seconds to close, with no buffeting and no pitch changes. Unhappy with the lack of built-in guns, as it was originally designed for high-altitude bombing rather than low-level close-air support, 8 Browning guns were mounted in the wings. Later, 4 20mm cannon were installed on most aircraft, and these were canted downward for convoy strafing. The Showran bombing system, APW-11 radar, APS-54 warning receiver all came as standard. These weapons modifications gave the B-57 capabilities the British original never had. The tandem cockpit also solved gunsight problems the offset British arrangement created, as the flat glass panels didn't flex under temperature changes the way curved canopies did. The Australian Canberra Mk.20 carried none of these modifications. It had no rotating bay, no forward guns, no radar warning. And it was an aircraft that was built to satisfy different mission assumptions that naturally determined different equipment choices. Whether the added complexity justified the added capability would only become clear once logistics couldn't be assumed and wars lasted longer than anyone planned for. But on paper in 1954, the B-57B looked better equipped than anything else available. In every category tested, Tibbs detected no difference from the British version or found that the B-57B superior. Though with a max speed of 582 miles an hour, it's 8 miles an hour slower than the B-57A with a max ceiling of 48,000 feet, 5,000 lower than an A-series sister. But that day, Tibbs' display was enough for Mikesh's earlier skepticism to evaporate completely. Years later, he wrote that Tibbs' demonstration was far more spectacular than Bemont's Andrews display, and that he was hooked on the aircraft forever after seeing what it could do. In January 1955, the 345th Bomb Group received its first B-57B 3 months after the demonstration that sold them on the aircraft. By April 1956, the 461st Bomb Group was fully equipped. Then suddenly, a month later, the entire B-57 fleet was grounded after a series of seemingly unexplained accidents, and the pattern was disturbingly consistent. Aircraft pitching suddenly into the ground during high-speed, low-level flight that crews seemed unable to prevent. Sometimes the aircraft would pitch up violently instead, climbing steeply before stalling and spinning in, equally fatal, just taking longer. The investigation teams had wreckage to examine, but not many survivors to interview. What they eventually discovered was a failure mode the British had already encountered and solved years earlier. The B-57's powered tailplane trim system used an electric motor to tilt the entire horizontal stabilizer, changing its angle of incidence relative to the fuselage. This was brilliant for trimming the aircraft across different speed and weight conditions when it worked, and when it failed, it became a death trap. The root cause was a sticky switch in a trim circuit. Under certain conditions, temperature, vibration, wear, electrical load, the switch could fail to release when the pilot let go of the trim control. The motor would keep running, driving the tailplane to extreme angles, nose up or nose down, creating pitch forces the elevator couldn't overcome. But that wasn't the only problem. The wiring design was fundamentally flawed. Power lines and signal lines ran together in a single bundle along the fuselage. Under the right conditions, such as electromagnetic interference from nearby systems, vibration causing intermittent contact, voltage fluctuations from combat damage, or electrical system failures, the power lines induced stray currents into the signal wiring. The system was giving itself commands the pilot never made. And there was a third issue. The actuator was too fast. When the trim system did fail, it would drive the tailplane from neutral to full deflection so quickly that pilots had no time to recognize what was happening, diagnose the problem, and take corrective action. At low altitude, where the B-57B was designed to operate, where crews were flying tactical profiles at 500 knots just above the terrain, there simply wasn't enough sky between the aircraft and the ground to survive even a few seconds of uncommanded nose-down trim. None of this was visible during the earlier demonstration flights, but only because the aircraft was new, the conditions were controlled, and the flight profiles relatively gentle. The British had discovered all three problems and had fixed them by separating the wiring looms and installed a new dipole trim switch. All this slowed the actuator and also restricted its travel limits. The reconfigured system had a failsafe whereby the pilot had to actively hold the switch before the circuit would energize. The fixes worked and the mysterious Canberra crashes stopped. Why the American engineers encountered the same problems years later remains unclear. Whether the information didn't transfer effectively across the Atlantic, whether the extensive American modifications obscured the relevance of British solutions, or whether different components created a false assumption that British trim failure wouldn't apply. Whatever the reason, American crews learnt the same lessons British crews had learnt years earlier, at the same terrible cost. Between May and September 1956, no B-57 flew tactically whilst engineers hunted for the cause of the failure the British had already paid for. The US Air Force eventually implemented nearly a dozen fixes, many of them eerily similar to what the RAF had already done. The stabilizer trim gauge, originally positioned on the lower side panel where pilots couldn't monitor it during high workload phases of flight, was relocated to a more conspicuous position directly in the pilot's line of sight. So if the trim is running away, the pilot needs to see it immediately, not after the nose is already pointing earthwards. A power cutoff switch is also installed right next to the gauge. In one motion, the pilot can flip the switch, kill the motor, and stop the trim movement. Simple, obvious, and absolutely critical. During testing, it was determined that at maximum speed with full nose-down trim, 80 pounds of pull force, well within the capability of any pilot, can hold the nose up until speed bleeds off enough to ease controlled pressure. It's manageable, barely, if you catch it immediately and know what you're fighting. Should the trim run to full nose up instead, the aircraft becomes uncontrollable above 350 knots. In this scenario, the pilot is trained to reduce the power to let the speed bleed off to where it becomes manageable while they deal with the trim, assuming they don't stall and spin in. At low altitude, neither scenario is survivable unless the pilot can react within seconds. The dive brake switch, originally hidden under the canopy rail, needing pilots to hold it throughout the full travel on the boards, converts to a simple two-position toggle easily actuated by thumb on the right throttle. If the pilot is fighting a runaway trim situation and desperately needs to slow down, they can't be fumbling under the canopy rail for a spring-loaded switch they have to hold. Even the canopy open-close switch goes through multiple iterations from push-pull to up-down shielded configuration after several canopies come open and off in flight. Not directly related to the trim problem, but discovered during the same intensive engineering review that asked the question, what else can kill the crews that we haven't thought about? The fuel control panel, for example, initially laid out like a schematic with identical knobs for every function, including engine fuel shutoff, proves too easy to misidentify under stress. It seemed that just having different colored knobs failed to prevent turning the wrong one when pulling Gs, scanning for threats, and trying to hold formation at low level. The engine shutoff and bypass functions eventually convert to safety wired switches and square pull knobs, different shapes, different motions, impossible to confuse even when you're not looking at them. No further accidents of this nature occurred after the grounding ended in September 1956. The modifications worked and the B-57B returned to operational squadrons with trim systems that wouldn't kill their crews. By early 1957, the fleet was flying tactically again. The aircraft Pat Tibbs demonstrated at Langley in October 1954, now proving safe enough for the missions it was designed to fly. Phan Rang Air Base, South Vietnam, October 1966. Eugene Young steps off the transport into heat that hits like opening an oven. Not the dry heat you might expect, but the wet heat, thick enough to taste, carrying smells that don't quite yet register. Aviation fuel, red dust, and something organic rotting in the monsoon humidity. He's Martin's senior systems engineer, here to keep the B-57s flying under conditions Baltimore never anticipated. The aircrafts he's supporting represent the accumulation of everything covered in previous chapters. The British design that worked, the American modifications that improved it, the institutional requirements that drove nearly 3,000 engineering changes, most minor on paper, but taken together reshaping how the aircraft behaved and was maintained. And now those modifications have to survive combat. Many of these requirements had been shaped by the expectations of a global war, not the grinding logistics-heavy counterinsurgency that Vietnam became. But the missions that would define B-57 operations had begun 18 months earlier, in April 1965. Ho Chi Minh Trail, Southern Laos, April 1, 1965. Two B-57s climbed through darkness to 30,000 feet, navigation lights extinguished, radio chatter minimal. Captain Ben Stone of the 8th Bomb Squadron leads the flight, his navigator behind him cross-checking TACAN fixes against the map. Below, southern Laos spreads invisible in the darkness, mountains, jungle, and somewhere down there, the supply routes filtering south from North Vietnam. The rendezvous point sits at 15,000 feet, where a C-130 Hercules circles, waiting to turn night into something tactically useful. This is Blind Bat, its rotating red beacon visible for miles. The two B-57s joined formation slightly above and to each side, using white lights mounted only on top of the transport to maintain visual contact. When the C-130 navigator spots the ferry crossing near Chipone, the formation descends together towards 8,000 feet as terrain permits. The C-130 commander calls out the countdown, 2 minutes to flares. The B-57s move off to the side, dropping 1,000 feet below the Hercules. 12 evenly timed flares eject from the C-130, deploying small parachutes as they descend. Moments later, harsh white light from the Mk.24 flares turns the jungle from darkness into geometric shapes. Trees become forms, roads become vectors. The tactical window exists in those few minutes as the flares burn. Stone's B-57 rolls in first. The rotating bomb bay, that brilliant American modification, opens, one 500-pound bomb away. Secondary explosions flash below on the ferry crossing. The second B-57 follows, drops its ordnance and climbs back into darkness. They cycle through the pattern whilst the flares last, 1 or 2 bombs per pass, maintaining pressure that denies them from crossing. This first night mission into Laos marks the beginning of Operation Steel Tiger, the campaign against enemy supply movements through southern Laos that will consume B-57 operations for the next 4 years. The mission assessment: 1 ferry boat destroyed, 4 trucks sunk with it, 1 bridge damaged, approximately 20 buildings destroyed by secondary explosions. The J-65 engines produce what crews call a weird whine all of their own. At 50% power, the sound shifts into a pulsating rumble beat that carries across the jungle. The enemy learns to recognize it immediately. When American and South Vietnamese intelligence interrogated Viet Cong defectors, showing them aircraft silhouettes, most pointed immediately to the B-57. The screaming bird, they would say. It is the worst, it stays over target long time, and it never runs out of bombs. The Vietnamese word they use is con sao, or worm. The most loathsome creature in all Vietnam, they called it. Not because of speed, not because of the bomb load, though both mattered, because it stayed. Not the quick passes that the F-100 Super Sabres made before running for fuel, 3 hours over target crawling around the sky like a worm. March the 15th, 1966, Chipone, Laos. Captain Larry Mason brings his B-57 into a strafing run at 400 knots, guns hammering at the truck convoy his navigator had spotted below. The hit comes without warning. The aircraft rolls nearly inverted. Mason fights the controls, regaining some semblance of flight, but the damage is catastrophic. In the navigator station behind him, Captain Jer Joyner is badly wounded in the arm and leg, bleeding heavily. The indicators in Mason's cockpit show chaos, one engine losing power, fire warning on the other, radio communication gone. Landing gear indications showing malfunction, left main and nose gear stuck in intermediate position, right main showing down. Joyner passes a bloodstained note forward through the gap between the seats. The note reads, "Hit badly, arm and leg, losing blood." The procedure is clear. Eject. Get out whilst the aircraft is still controllable. But Mason later recalled, believing his navigator's wounds were too severe, that Joyner wouldn't survive the bailout, the parachute opening shock, the jungle landing, the time before rescue could arrive. He refused to eject. Instead, he nurses the crippled bomber towards Da Nang, 90 miles away. No radio to call ahead, no way to verify his gear situation. Preparing mentally for what he thinks will be a gear-up belly landing. What Mason doesn't know, the same AAA that destroyed his cockpit indicators also forced all 3 landing gears to drop and lock. The erroneous cockpit indication is showing failure where the gear has actually deployed correctly. On his 3rd pass at Da Nang, convinced he's about to belly it in, Mason places the gear handle in the up position and commits to the landing. The aircraft touches down smoothly on extended wheels he thought were still retracted. Joyner survives. Mason receives the Air Force Cross, the only one awarded to B-57 operations, the first given to a living recipient in that war. Aircraft 906, shot nearly to pieces over Chipone, is repaired. It will fly nearly 3 more years of combat operations before being modified as a B-57G for the final evolution of night interdiction. The modularity that makes the repair possible, replacing damaged sections with components from other airframe, came from Teddy Petter's 1945 design philosophy. 37mm and 57mm anti-aircraft batteries start to appear at choke points, river crossings where interdiction concentrates. The flares that illuminate targets also silhouette the B-57s at certain points during attack runs. Ground fire strategically positioned along supply routes exploits those moments when the aircraft becomes visible against the white light. Close to the ground during attack runs, the B-57s run the gauntlet of automatic weapons fire. Many aircraft come home with tail sections riddled, some don't come back at all. The B-57, proving its ability to sustain combat damage and return crews safely, becomes noteworthy enough that when the first crew successfully ejects, it makes operational history. June the 8th, 1965, in the delta west of Canto, Captain Gordon Nelson and Captain James Carnes takes a hit on their third dive bomb pass. The left wing bursts into flame. Despite the engine shutdown and fire extinguisher activation, it didn't stop it. They eject and are picked up by helicopter only 4 minutes and 19 seconds after they hit the ground. Phan Rang, October 1966. Gene Young stands on the ramp watching aircraft cycle through operations that demand more from systems than Baltimore ever tested. The rotating bomb bay proves its worth night after night, exactly the capability that justifies its complexity. For now, the screaming bird circles overhead, seemingly endless bombs taking out the enemy supply columns. The crews trust the aircraft will bring them home, and between mission, Gene Youngs coordinates the logistics that make it possible. The night doesn't belong to anyone exactly, but for 3 hours at a time, whilst fuel and bombs last, the B-57 can make the NVA pay rent. Phan Rang Air Base, South Vietnam, March 1967. Gene Youngs watches the crew chief hunch beneath aircraft 863, wrestling with a bomb that won't quite fit. The Canberra sits low to the ground, that elegant British design built for high altitude and handling, not for working underneath in 100-degree heat whilst manhandling 500-pound ordnance into a rotating bomb bay. The chief has maybe 18 inches of clearance. He's on his back, sweat already soaking through his flight suit, trying to align the shackles whilst an armourer steadies the bomb from the side. Martin's engineering drawing showed this 17-foot rotating door being preloaded at a remote site, rolled to the aircraft, lifted into position with 4 handheld hoists. Rapid mission turnaround, very elegant solution. The rotating bay itself works brilliantly, opens up 500 knots, no buffeting, no pitch changes. One of the few American modifications that really improved the aircraft, but using it now needs procedures Martin never designed for. That gap between engineering theory and operational reality. Youngs has been documenting it for 6 months now, watching modifications interact with each other and with Vietnam in ways the institution couldn't predict. None of these choices were irrational on paper. They reflected priorities that assumed stable bases, predictable logistics, and short wars. The crew chief finishes, slides out, nods to the armourer. Next bomb. 8 more to go before this aircraft cycles back into the night. 4 aircraft down this morning, not combat losses, just maintenance. Aircraft 863's LOX system failed recharge. There's a leak somewhere in the plumbing, probably corrosion, definitely needs troubleshooting before tonight's mission. And then there's aircraft 517's aborted engine start. The cartridge fired, but the turbine didn't catch. Now the crew chief is pulling the starter, cleaning contact points fouled by propellant residue, installing a fresh cartridge. 10 minutes if everything goes smoothly, longer if the contacts need serious work. And 806's canopy actuator is sticking. The one-piece plastic greenhouse that provides excellent visibility also weighs more than the British bubble it replaced, stresses the hydraulic differently, accumulates heat that degrades seals faster than peacetime operations ever tested. And 551, well, 551 is why Youngs is here. The 19-foot chord wing arrived last week. Special railcar from Davis Moffin in Oakland. Ocean vessel to Cam Ranh Bay, convoy escort to Phan Rang. The crate was so large, Youngs initially thought it was a Vietnamese house being relocated. Installing it needs precision he's not certain the field's facilities can deliver. The original wing burned off during takeoff back in January, not combat damage. A detached engine tailpipe during takeoff damaged the wing spar. The pilot, Royce Tate, managed to make an immediate landing, saving the aircraft and crew. The wing spar itself, that massive forging the British designed to carry ultimate loads of 7.5 Gs through the two bolt attachments, was severely damaged enough that no field repair could restore structural integrity. So they're replacing the entire wing rather than rebuilding it. They had pulled the donor aircraft 552 apart in Arizona storage, shipped its wing halfway around the world, and will now install it onto a different fuselage. This is Teddy Petter's modular construction philosophy, working exactly as designed. 5 independent structures that can be mixed and matched at final assembly or 20 years later in Vietnam. Alignment tolerances measured in thousandths of an inch. Young's coordinates it all whilst managing the daily crisis of keeping aircraft flying. The LOX facility sits at the edge of the ramp, ugly and functional. Every aircraft needs topping off before flight. The British use gaseous oxygen bottles, swap them when empty, no special facilities required. The Americans specified liquid oxygen to save weight. This is sensible on paper. LOX weighs less for equivalent capacity. But in practice, LOX needs factory-like facilities maintaining -297 degrees Fahrenheit, specialized transfer equipment and technicians in protective gear servicing one aircraft at a time. 10 minutes per aircraft once connected. Right now, 3 aircraft are in the queue for recharge. The facility can handle 1 at a time. Simple math says that the 3rd aircraft waits 30 minutes minimum, longer if there are complications. Operational flexibility, traded for weight savings, the specifications prioritized. In 1965's at Tan Son Nhut, 18 B-57s maintained a flying rate 46% above planned wartime tempo. The aircraft worked and the maintenance burden was manageable. But the question was whether that tempo could be sustained once the war stopped being temporary and started being permanent. The cartridge starter problem is different but related. Every engine start consumed 1 cartridge. The cartridge ignites, drives the turbine, spools the engine. The electrical contact points are fouled with propellant residue and the cartridge is spent. Removing the spent cartridges, cleaning the contacts, installing a fresh cartridge, crew chiefs call it the grimmest job on the aircraft. Later British marks mitigated this with triple breech starters, so with 3 cartridges, if the first one fails, immediately try the second one. The Americans retained the single-shot design from earlier variants, which meant that the pilot had 1 attempt. If it fails to spool the engine, means swapping for a new cartridge. And the smoke? 10 seconds of dense black cloud erupting from the engine during ignition. Acrid, toxic, visible across the ramp. Inexperienced fire guards see it and think the aircraft is burning, that trigger alarms that scramble crews, only to be told it's not a fire, it's just starting. Some optimists had suggested the smokescreen might be useful in wartime. But the heat is the invisible enemy. That one-piece blown plastic canopy provided exceptional visibility and was critical for the tandem cockpit arrangement to solve the problem with gun sight harmonization. But under the tropical sun, it becomes a greenhouse. Ground temperatures regularly exceed 100 degrees Fahrenheit. Inside the cockpit, 120 degrees is common, and 130 isn't unusual. Crew climbing in for pre-flight find their suits already damp with perspiration before engines start, and the instruments are too hot to touch, switches that burn fingertips even through Nomex gloves. The British bubble canopy wasn't perfect either. RAF crews in Singapore complained about the greenhouse effect, but it was smaller and 400 pounds lighter, plus it was also fixed in place. Those extra pounds and their hinged setup create maintenance problems in unexpected ways. Heavier canopy means stronger actuators mean more complex hydraulics mean more seals, and more seals in tropical heat means more failures. Aircraft 906's stuck actuator this morning traces back to steel degradation, accelerated by heat cycles the system was designed to handle, but not at the duty cycle Vietnam demands. The solution is mobile cooling units, ground equipment that blows cold air into the cockpit during pre-flight, trying to bring temperatures down to merely uncomfortable rather than dangerous. More infrastructure, more logistics, more constraints on where the aircraft can operate and how quickly they can cycle. The British designed for simplicity. The Americans designed for compliance. Young stands beside aircraft 551 watching the wing installation. 3 technicians on stands aligning a full bolt attachment. The work is precise but slow. The British system attached each wing spar directly to the centre fuselage through 2 massive bolts. 20,000 hours between major structural work, they claimed. The Americans, however, redesigned it as a full bolt affair. More redundancy, better fatigue characteristics, different engineering priorities and also different maintenance requirements. Hobday had called it needlessly complicated. Right now, watching the installation, Young sees Hobday's point. The 4-bolt system isn't better or worse, it's different. Extra attachment points create alignment requirements, complexity demands time. In factory conditions with proper tooling, probably manageable. In field conditions at Phan Rang with improvised stands, the work stretches into weeks. And 551's wing failed anyway. Of course, not structural failure, fire damage that the 4-bolt attachment couldn't have prevented and wouldn't have prevented, and has nothing to do why this wing needs replacement. The modularity that's saving 551 comes from English Electric all the way back in 1945. The 4-bolt attachment comes from the Wright Air Development Center in 1952. One makes the repair possible, the other one makes it complicated. 94 B-57s deployed to Southeast Asia, 51 were lost to enemy action, 7 to other causes, but those numbers don't capture what exhausted the fleet. The decline wasn't combat alone. Missions flown harder than specifications anticipated, defences adapting faster than tactics could counter, and a tropical climate that degraded systems at rates peacetime testing never predicted. These all played their part. But maintenance complexity, the daily accumulation of small failures that individually seemed manageable but collectively reshaped operational capability, these made the numbers far worse. The lock systems needing daily recharge, cartridge starters fouling every engine start, canopy actuators degrading due to heat. But the aircraft work. 863's bomb load is complete. The crew chief slides out from beneath the aircraft for the last time, stands, stretches, his flight suit is black with sweat, his hands stained with cosmoline from the ordnance. The rotating bomb bay closes smoothly, hydraulics functioning exactly as designed. In 6 hours over Laos, it will open at 500 knots, releasing its contents. The one modification that works brilliantly, surrounded by 2,799 others that mostly just complicate things. Youngs makes his notes for his weekly report to Baltimore, wing installation proceeding on schedule, locks facility handling the load, cartridge starter inventory adequate. 3 aircraft down for maintenance, but available if needed. Everything working exactly as the system predicted, just not as efficiently enough to keep 94 aircraft operational when specifications never quite accounted for these conditions. For now, the night belongs to whomever can sustain the logistics. At the far end of the ramp, 8 Australian Canberras sitting beside American B-57s are about to show that simpler can be sufficient if sufficient is enough to actually win. Phan Rang Air Base, South Vietnam, April 1967. 8 Canberra Mk.20s from the Royal Australian Air Force No. 2 Squadron taxi past the American B-57s, parking in the sections allocated by the 35th Tactical Fighter Wing. On the ramp, the visual distinctions are obvious. These Canberra Mk.20s, their tails marked with flashes, are Australian-built Canberra B-2s, constructed under license to British specifications with only minor incremental changes. The Australian aircraft do have some updates, such as improved corrosion protection and wingtip bomb carriers, but overall very similar to the machine Roland Beaumont flew at Andrews in February 1951. The Mk.20s kept the offset pilot, the side-by-side navigator and bomb aimer, the glazed nose for visual bomb aiming and the side entry hatch rather than the canopy access and the traditional clamshell bomb bay doors instead of the rotating rack. What the Americans had spent 28 months modifying to meet institutional requirements, the Australians built to original specifications and flew operationally for 16 years before deploying to Vietnam. Their mission in Vietnam is laid out by Wing Commander Rolf Aronson in a matter-of-fact aircrew brief, typical of the Australian manner. The squadron, call-sign Magpie, will fly roughly 8 sorties per day. Combat sky spot at 20,000 feet using ground radar direction and boomer missions for daylight visual bombing with forward air controllers marking targets with smoke. Both missions require precision level bombing using a bomb sight in the glazed nose where a dedicated bomb aimer lay prone, feeding altitude and airspeed data into the World War II vintage computing mechanism. The USAF officers coordinating joint operations are polite but skeptical. High-level bombing in a tactical environment with a bomb sight that predates Korea? The Australians know what they are doing and demonstrate what skepticism misses. 19th November 1967, Dak To. Wing Commander Aronson, flying with another Canberra, has been briefed for a radar bombing mission. At the last moment, the mission was cancelled, but rather than return to Phan Rang without dropping their ordnance, they requested alternatives. Quickly, a call came through, an urgent task to Dak To, much further north. With no other customers calling, they agreed, knowing they would need to land at nearby Pleiku for refueling afterwards. 4 North Vietnamese regiments had been sent into action near Dak To, just miles from Laos and Cambodia, and the fighting was particularly heavy with the local forces reinforced with American and South Vietnamese units. The forward air controller briefed Aronson on a specific problem: enemy troops firing from one side of an 8,000-foot ridge onto friendly forces on the other. There was little margin for error. The FAC marked the target with smoke. Both Canberras bombed directly on the marker, each dropping 6 American-made 750-pound bombs in calculated sticks using their World War II-era bomb sights. When they landed at Pleiku for refueling, they met the FAC who had marked the target face to face. His assessment was, in one word, magnificent. After the Canberras departed, friendly forces didn't hear as much as a peep from the enemy guns and mortars. 2 aircraft, 1 pass each, and the problem was solved. Precision level bombing works when you understand the mathematics and trust your equipment. The Dak To strike demonstrated what level bombing could do when conditions cooperated. Flat terrain meant clear altitude data, and stationary targets gave the bomb sight time to calculate. A forward air controller that marked precisely where bombs needed to land. But these weren't the conditions that American B-57s encountered over the mountainous Laos at night. The Royal Australian Air Force increasingly concentrated on the Mekong Delta missions, where terrain was at or near sea level, and this gave the bomb sight precision that the mountainous regions never really allowed. The geography mattered as much as the technique. The Canberra's level bombing missions worked brilliantly as the Delta's flatness eliminated variables that complicated operations elsewhere. The American B-57s flew different missions in different terrain against different threats. Both approaches worked, and neither was universally superior. The missions determined which variant proved more suitable. Combat Sky Spot continued alongside boom operations, but daylight missions eventually accounted for 50% of squadron effort because forward air controllers kept requesting them specifically. It wasn't long before FAC started requesting the Canberras by name. Some even called them the A1 of the jets, comparing the bomber to the Douglas A1 Sky Raider for its precision and reliability. And by 1969, 70% of the Royal Australian Air Force's missions concentrated in the Mekong Delta. Flat terrain meant clear altitude data, and stationary targets gave the bomb sight time to calculate. But by then, the American B-57s were already gone, withdrawn in 1969 after the fleet became operationally exhausted. The Australians would continue flying from Phan Rang until 1971. But right now, Gene Youngs watches the Australian ground crews work in their aircraft with noticeably different procedures and requirements. The Mk.20s use gaseous oxygen bottles. They swap them when empty, and no LOX facility required, no daily recharge cycle, and no technicians in protective gear handling -297-degree fluids. The cartridge starters on the A1s were also smokeless, so no more dense black smoke, with some of the later arriving Australian aircraft having those triple breech systems. So again, if the first cartridge failed, they could immediately try the second one. The bomb loading methods differ fundamentally. The American B-57s with the brilliant rotating racks but dependent on specialised equipment, whilst the Australian Mk.20s with traditional bomb bay doors that let the armourers work with slightly better access and more room. Neither approach is obviously outright superior, but the question is which approach works with less infrastructure, fewer specialists, and simpler logistics. However, the sustainability difference was more than just oxygen bottles and starter cartridges. The Australians' 8 aircraft squadron depended entirely on USAF infrastructure at Phan Rang. The 35th Tactical Fighter Wing provided base operations, logistics support, maintenance facilities, and defensive positions. When American policy shifted towards withdrawing US forces and transferring operations to South Vietnamese units, the Vietnamization program, the 35th TFW prepared to leave. Without that support structure, 8 Canberras couldn't operate independently from an exposed base in hostile territory. The Australians sustained operations for 4 years, flying 8 sorties daily, a tempo mutually agreed with the 7th Air Force, not imposed by operational demands. Predominantly high-altitude radar bombing and level attacks in the flat Mekong Delta, where the Canberra's characteristics matched the mission perfectly. The American force faced different mathematics. 94 aircraft cycling through low-level interdiction over mountain and sloughs, higher sortie rates, and they were also exposed to ground fire at altitudes between 4,000 to 8,000 feet rather than 20,000 foot radar runs. By October 1969, the 8th and 13th Bomb Squadrons had only 9 total aircraft combat ready. The attrition wasn't just combat losses, there was the operational tempo above the planned rates and the tropical climate that degraded systems faster than peacetime testing had predicted. Taken together, these all contributed to exhausting the fleet. The Australians sustained that tempo for 4 years whilst delivering 76,000 bombs, with such precision that some crews occasionally sustained battle damage from their own bomb debris. For 3.5 years, No. 2 Squadron operated without a single combat loss. Then, on the 3rd of November 1970, aircraft Alpha 84-231 disappeared during a combat Skyspot radar bombing mission over Da Nang. Flying Officer Michael Herbert and Pilot Officer Robert Carver were lost to the aircraft. The wreckage wasn't discovered until April 2009 in dense jungle near the Laotian border. Their remains were repatriated to Australia on the 31st of August 2009. On the 14th of March 1971, Wing Commander Downing and Flight Lieutenant Pinchers were hit by a SAM missile in the northwest corner of South Vietnam. Both crew ejected and spent the night in the jungle before helicopter recovery the next morning. They survived, but the incident forced operational restrictions that hadn't existed before. The 7th Air Force directive was clear. No aircraft without SAM detection equipment could operate in high-threat areas. Since the Australian Canberras lacked the electronic warfare systems that the American B-57s carried as standard equipment, they were withdrawn from high-risk areas. A technology gap, not a design flaw. The steady 8-per-day sortie rate continued until the 35th Tactical Fighter Wing began to withdraw. The Australians flew their final combat sortie on the 31st of May 1971, the 11,963rd mission of No. 2 Squadron's 4-year deployment. 4 days later, on the 4th of June 1971, the Australian Canberras fitted with long-range tanks departed Phan Rang for Australia, home to Amberley. Both forces faced the same tropical climate-degraded aluminium, hydraulics and seals at rates that peacetime specifications never anticipated. Both flew variants of the same basic airframe that Teddy Petter had designed all the way back in 1945, with the same fundamental strengths and underlying limitations that no amount of modification could completely eliminate. The difference between the two aircraft showed up in the maintenance logs rather than the specification sheets. The institutional modifications that made the B-57 American delivered capabilities the Air Force valued: better gun sight harmonization, improved escape provisions, rapid ordnance turnaround through that rotating bomb bay, tandem cockpit visibility for the attack profile, cable controls that maintainers understood, and the 4-bolt wing attachments with better theoretical fatigue life. Ultimately, the British built it simple, and the Americans built it compliant. Gene Youngs files his final weekly report to Baltimore. Everything worked, just not efficiently enough to keep aircraft operational when the war stopped being temporary and started being permanent. The variants that followed told different stories. However, these flew different missions, different modifications, and had different priorities. These are stories for another time. Gene Youngs locks the maintenance hangar for the last time. The screaming birds are now gone. And there we have it. Now, I know what some of you are probably thinking. Joe, what about the RB-57D, the WB-57F, the B-57G, and all those other variants? Well, fair point. And yes, there are stories there, remarkable ones actually. And those are stories for another day, and perhaps maybe another 3-part series, if I'm being honest, because each variant deserves proper treatment rather than being crammed into an epilogue that nobody asked for. What matters is that we've covered the core story, the design philosophy that made this aircraft possible, the operational reality that proved that it worked, and the institutional forces that, well, that kind of shaped how both Britain and America used it. Everything else, I'd rather do them justice properly than rush through them just to claim completeness. So this isn't the end of the Canberra story on this channel. It's just the end of this particular telling. And honestly, spending the better part of 4 months researching one of my all-time favorite aircraft has been, well, it's been exactly the sort of deep dive that makes this kind of work worthwhile. The Canberra has always fascinated me, not just because she's British, because she represents something increasingly rare in modern aviation, a design that was fundamentally sound from the start, adaptable without being overcomplicated, and genuinely loved by the people who flew her. And it's been very satisfying to piece together how one aircraft served so many different masters in so many different wars. And to those of you who are stuck through all 3 parts, some of you watching this for over 4.5 hours, 5 hours maybe, thank you, genuinely thank you. I know that documentary length content on niche aviation topics isn't exactly algorithm friendly, and I appreciate you giving these videos the time that they needed to brief properly, rather than have one video in 20 minutes that goes through all the different variants. And to anyone who's discovering this series now, possibly years after it was first posted, hey, maybe you're watching this 30 years from now and I'm up with the angels on my cloud, my own set of wings, maybe straight wings like the Canberra. Welcome, pour yourself a cuppa, get comfortable. So what's next? Well, I've got a bunch of scripts that have been glaring at me from my desk for over 6 months now. I mean, I've got a couple of scripts here which have been sat on my desk for nearly a year, and I need to get round to them. There's more stuff coming. But for now, thank you for watching. Thank you for your patience with these longer videos. And I'll see you in the next one. Toodaloo.